In this video, we're going to be doing hypothesis testing with 2 samples, and we're going to be using Rguroo. So far, all the hypothesis tests that we've done have dealt with one population, where we took one sample and we tested the mean, or we tested the proportion about that single population. But now we're going to compare 2 populations by comparing their means or comparing their proportions. So here's an example. If you wanted to compare the proportion of Democrat voters in 2 different states, you could perform one of these 2 population tests. So you can compare the sample means of both states, but again, that's only a sample, and that's a representation, yes, of the population, but is it the best we can do? This is where the hypothesis test comes in. So in this chapter, we're going to be comparing 2 population parameters, or a parameter from 2 different populations, and we're going to do that by doing these 2 population tests where we take 2 samples. So the types of 2 population tests will look very similar to the 1 population test we did. We did population inference. I'm sorry, not population inference. It starts with a P. Proportion inference. We did proportion inference, and we did mean inference, but we only did it for 1 population. Now we're going to expand it, and we're going to do proportion inference and mean inference for 2 populations. So when you go to analytics and click on the analysis tab in Rguroo, the very first 2 things say proportion inference and mean inference. This is something you should know. When you click on each, a side menu pops out, and for these tests, rather than click 1 population, you're going to click 1 and 2 population. So okay, so let's look at a few of differences that you're going to see in these type tests that are different than what we saw in the 1 population test. So first, once you identify the claim in which you are comparing these 2 population parameters, you are going to write the null and the alternate statement slightly differently. Now, the null is still an equality statement, but rather than to compare the mean to some parameter number, such as, we're comparing the mean of the cereal boxes to 20 ounces. So for the null, we would write the mean equals 20. Instead of doing that, we're going to assume that for our null, that the mean of the first population and the mean of the second, or proportion of the first and the proportion of second, are the same, that they're equal. Because remember, the null is always an equality statement. So we're going to assume there is no difference. So to write that, you would either write mean 1 is equal to mean 2, so mu1 equals mu2 for the null, or if it's proportion, you're going to write capital P1 equals P2. Now, you can also replace those numbers to the side. Like normally you write it like this: mu1 as a subscript equals mu2. But let's say we were doing the mean of the heights of women, and we're comparing it to the mean heights of men. You could write it like this: the mean of women is equal to the mean of men. So what I'm saying here is, rather than using numbers to represent the populations, sometimes we can use letters to represent our population. So it helps us to identify which population is which. Now for the alternate is similar to the alternate statements from before, or H1 or HA, depending on how you write it. And you're either going to say that the first mean, or the mean of the first population, is less than the mean of the second, the mean of the first is greater than the mean of the second, or the mean of the first is not equal to the mean of the second. And same thing with our capital P's for proportion. So technically, the 3 types of tests that you can run for 2 population tests that we're going to be doing in our class is 2 population mean inference. So that's mean inference choosing 1 and 2 population, and we're going to focus on the 2 pop. two population proportion inference, and then we have a two population mean inference where the data is what we consider paired. So we're going to be talking about that. All right. So now everything else is exactly the same that we did before. You're going to find the p-value. Once you run the test, you're going to compare the p-value to the significance level. And then if the p is low, the null must go. So if the p is less than or equal to the significance level, we reject the null. If it's greater, we fail to reject the null. And then we write our conclusion. So if we reject the null, there is enough evidence to conclude H1 is true. And you must write that in context. And if we fail to reject the null, there's not enough evidence to conclude that H1 is true. So lots and lots of similarities to what we have already done in the past with hypothesis testing, and just a few differences. All right, so let's look at what the screen looks like in Rguroo when you run one of these tests. It will look slightly different, the box that pops up when you click on 1 and 2 population. So again, we go to Analytics, we choose, or we click on the Analysis tab, and in the drop down, we either choose Mean Inference or Proportion Inference. And then we'll choose 1 and 2 population. It's 1 and then the and symbol, 2 populations. So then you're going to get this box. So if you are doing this with a data set, you would click the here and choose the data set and choose the two variables that you're comparing. However, most likely what you're going to need to do is you're going to need to put the data in here. And so you notice we have 4 tabs here at the bottom, on the bottom half of the screen of this box. So you've got Summary, Population 1, Population 2, Population 1 to 2. We're going to focus on Summary and Population 1/2. All right, so Level is a drop down that I believe only works if you select a data set. So we're going to skip to Label, and you're going to label what each of the samples represent, what population they represent. So let's say we were doing that Democratic example from a few slides ago. You could say the Democrats in Maryland would be the first population, and Democrats in Virginia would be the second population. You would fill in your sample mean for each population, or for each sample from that population. And then most likely you're going to be given the sample standard deviation rather than the population standard deviation. So you would fill that in, and then you would fill in the sample size. Okay, so the first step is just filling in what we know, what we've been given. Then you're going to skip over to the population 1 and 2 tab. And you're going to enter the significance level. You're going to put in what H1 is, and you're going to click T-stat most likely for the mean inference to population test, because you would only choose the Z-stat if we knew the population standard deviations of each population represented, but that's usually not the case. So we're going to choose T-stat. Also, when you get to the 1 and 2 population tab, it's going to ask you, one of the boxes that you can check is that the variances are equal. Normally, these will not be equal, but please carefully read your problems through, because sometimes it will tell you in the problem that the variances are equal. And so if they are, you want to make sure you check that box. Now, it's not here on this little screen. It's when you click population 1-2. The other thing I wanted to let you know is for H1, in Rguroo, it's on this page here, population 1-2. It'll say mu1 minus mu2. It'll have a box. Let's see. It'll have a drop down and then a box. Okay. So in the drop down, you are going to choose, and let me just draw a little box. So you're going to choose less than, greater than, or not equal to. In the box, you are going to put 0. And the reason is this, okay? So if, let me go back up here. So let's say that this is the alternate statement that we wanted. Let's say we wanted to say that the mean of the first population is less than the mean of the second population. Well, what happens? If I were to subtract the two, I should get a negative number if the first population mean is really smaller than the second population mean, which means if it's a negative number, it would be less than 0. If the mean of the first population is greater than the mean of the second, when I subtract mean 1 minus mean 2, I should get a positive number, which means it would be greater than 0. So you're still using the less than and greater than signs like you would before, but the number that you're going to put in for these is 0. And the same thing, if you're using the not equal to sign, you would use the not equal to sign here. Okay, so let's go to example 1, comparing diets. Are low-fat diets or low-carb diets more effective for weight loss? A sample of 77 subjects went on a low-carbohydrate diet for 6 months. At the end of that time, the sample mean weight loss was 4.7 kilograms, with a sample standard deviation of 7.16 kilograms. A second sample of 79 subjects went on a low-fat diet. Their sample mean weight loss was 2.6 kilograms with a standard deviation of 5.90 kilograms. Can you conclude the mean weight loss differs between the two diets? Use the alpha equals 0.01 level of significance. So here's what we're trying to conclude. So that the mean weight loss differs between the two diets. So one big clue that this is a 2 population test is that they took a second sample. A second sample was taken. So we're testing the means. So this is going to be a 2 population mean inference. All right. And so we're going to start by writing our null and our alternate statement. Now, since we're doing a mean inference, we are comparing means. So we're doing the mean of the low carbohydrate diet. So I'm going to write mu L and the mean of the, and actually I should write mu LC for low carbohydrate and the mu LF for low fat. And so for the null, we're going to assume that there's no difference and that they're equal. For the alternate, we're going to look to our claim. They're claiming that the mean weight loss differs. Now, it doesn't specify how it differs. It just says differs. So if they don't specify less than or greater than, we're going to do not equal to. So there we have our null and our alternate statement. We were able to write it fairly quickly. We didn't have to worry about setting anything equal to a specific number and getting confused about what number goes there. It's just mu of the low carb diet is equal to the mu of the low fat diet, and the mu for the alternate statement, mu of the low carb is not equal to the mu of the low fat. All right, so now when we run this test, it's going to ask us for a sample mean of the low carb and a sample mean of the low fat. It's going to ask me for a standard deviation of the low carb for the sample standard deviation, and sample standard deviation of the low fat, the sample size of the low carb, and sample size of the low fat. It's going to ask for all of those things. So we're just going to go through and find them. A sample of 77 subjects were on the low carb diet. So that is my N of the low carb. At the end of that time, the sample mean was 4.7 with a standard deviation of 7.16. All right. Now, moving on to low fat, it says a second sample of 79. So 79 is my N for low fat. The sample mean was 2.6. And the standard deviation was 5.90. All right, so we also need to remember that our significance level is 0.01. So let's come over to Rguroo, and we're going to click on Analytics, and we're testing a mean, so mean inference, but we're doing two populations because we have two samples. And we have this box that pops up. Now, we're not going to do anything here at the top because we're not using a data set. We're entering our own data. So we're going to come down here to the Summary tab. We're going to skip to Label. And the first population is low carb diet. And the second population is low fat diet. So you want to make sure that you label those. And then just fill in the sample mean, 4.7, sample standard deviation, 7.16. We don't know the population standard deviation, but the sample size is 77. And for the low fat, the sample mean was 2.6 with a sample standard deviation of 5.90 and a sample size of 79. And so just double check your numbers and make sure you enter them in correctly. So once you enter these in, then you're going to skip over to the population 1 and 2 tab. Just if you want to look, population 1 is where you could run a one population test on just the low carb diet. There's a confidence interval tab and a test hypothesis tab that looks just like the ones we did for one population. Same thing for population 2. But we want to run it where we're comparing the two. So we're going to skip to population 1 and 2. We're going to go test hypothesis. The significance level is 0.01. And we're going to say we believe that they're not equal to each other. And remember, I told you the number to put here is 0 because it says alternate hypothesis mu1 minus mu2. So if I were to subtract the 2 and there was a difference, that means the difference would not equal 0. And then you're going to choose T statistic because we know the sample standard deviations. And then over here, you would potentially click equal variances if it specified that the variances were equal, but we're not going to do that. If the data was paired, we would click there. This is not paired. We'll talk more about paired in another video. And that's basically it. I'm going to go ahead and click the confidence interval as well. And since we're doing a 0.01 confidence level, I'm going to do a 0.99. I'm sorry, since we're doing a 0.01 significance level, I'm going to do a 0.99 confidence level and click T statistic, and then I'm going to hit preview. You do not have to do the confidence interval, but I wanted to go ahead and do one so we could discuss it because the confidence intervals, when you are dealing with two populations with two samples, is slightly different. We look at it a little bit differently than we look at the ones for one population. All right, so you'll notice some of the same things in the data summary. You'll notice there's 2 rows, and that's because we have 2 samples. This is a sample for the low carb diet and for the low fat diet. If we go to the next row, you're going to see that we have, if they ask for test statistic, you have that here, but what we're really looking for is the p-value, and you can see where they've also graphed the p-value. You can see these are 2-tailed tests. All right, so our p-value is 0.0477. 0.0477. Okay, so let me go, and then let me go ahead and write real quick. Let me write down the confidence interval. This is 99%, and it is negative 0.645 and 4.845. So I'm going to write that down for later. All right, so let me go back to my screen where I was writing so that you can see that. Okay, so this was the p-value right here. And it is, when we're comparing, it is greater than our significance level of 0.01. It's greater. And so what do we do when it's greater? We fail to reject the null. Okay, so if we fail to reject the null, then that means there is not enough evidence to conclude that the mean weight loss differs between the two diets. All right. So we can't say that there is a difference, which means they might be equal. We can't say that either because, we're not allowed to accept the null. But we know we don't have enough evidence to say that they are different. All right, so let's see if our confidence interval agrees. So here's the deal with confidence intervals, okay? Confidence intervals for two populations. What you're finding the confidence interval for is you're estimating actually the difference in the means or the difference in proportions if you're doing a proportion inference rather than just an individual mean or an individual proportion. Okay. Now, the great thing is you could come back here. I'm just going to show you. If you wanted to, you could go back to each of those populations and do an individual confidence interval for the first population and the second population and estimate both fairly quickly. But you can also do a difference in the two population parameters. Okay, so that's what is actually found here when we found this there. So the template's very similar with one change. Remember you put your confidence level there, percentage. We're 99% confident that the true mean the true difference in the mean weight loss of the two diets is between negative 0.645 and 4.845. So here's the difference between the one population and the two population. All right, here are the parts that are the same. We are 99% confident. Let me do a different color here. We are 99% confident that the true difference in the mean weight loss, that's different. Because before we said that the true mean of weight loss, this is the true difference in the mean weight loss. So difference in the means or difference in proportions, if you're doing a proportion inference, is between this number and this. So all that's the same. This is the part that's different. You want to make sure that you are showing that you're estimating the difference in the means or the difference in proportions. And of course, writing that in context. So the means of what? But you are estimating the difference in the means. The difference in the means or the difference in the proportions. That's what you're estimating. So what does this really show? Like, what do we care about the difference? Well, here's the deal. If you will recall what we were saying up here, if you subtract the first mean minus the second mean and you get a number less than 0, a negative number, if you will, then that means that the mu1 is less than mu2. If the first number is greater than the second number, when you subtract the 2, you'll get a number bigger than 0, so you will get a positive number. So if you have two negative numbers, let me make a little box here. Confidence interval for, let me just write, this is for 2 population. That's important. If you get 2 negatives, this means mu1 is less than mu2. If you get 2 positives, that means that mu1 is greater than mu2. So if you get a negative and a positive, it means that mu1 most likely is equal to mu2. Now, again, we can't say that's definite, but most likely it is. So, and that's because 0 is included. So this here, because we have a negative and a positive, it implies that there's no difference between the two. And what did we say? There's not enough evidence to conclude that the mean weight loss differs. So we're saying in our conclusion that there's no difference. And that's what this implies, the confidence interval implies, because the difference is between a negative and a positive number, and 0 is included within that, which means there is most likely no difference. All right, so let's look at the next one, birth order. And we have 2 sets of data that you're going to have to enter into Rguroo. It says, in a study of birth order and intelligence, IQ tests were given to 18 and 19-year-old men to estimate the size of the difference, if any, between the mean IQs of firstborn sons and secondborn sons. The following data for 10 firstborn sons and 10 secondborn sons are consistent with the means and standard deviations reported in the article. It is reasonable to assume the samples come from populations that are approximately normal. And then they list the data. Can you conclude that there is a difference in the mean IQ of firstborn and secondborn sons? Use 0.01 level of significance. All right. So we're going to put this data into Rguroo. So I think I may have it in here already, but let me look. Well, here, I'll look at it this way. Firstborn. So that's IQs of first and secondborn sons. So let me pull that up. So yes, I did enter that already. So just to remind you how you put that in, you go to data import, do create data set, and then if you want to add multiple variables, you can. So I just put both samples, one sample in one column and in the other sample in the second column, label the variables and save it. So that is what I did. So it's IQ of first and secondborn sons is what I have mine as. So you can pause the video and go ahead and type those in for yourself as well. All right, hopefully you have those. So let me go back to here. So we're going to start by writing the null and the alternate statement. We're doing the mu of firstborn and the mu of secondborn sons. So actually for firstborn and secondborn, I might just go ahead and do mu1 and mu2 because that makes sense, right? Firstborn, secondborn. But for the alternate statement, we're going to say that mu1 is not equal to mu2 because we're trying to show that there's no difference. And we're going to do a 2 population mean inference. And you've got a couple of options. So if you've got the data in Rguroo, you can just go straight and choose the data set. I'm going to show you how to do that. The other way you could do it is you could do a numerical summary and find the mean and sample standard deviation of each one, and then manually enter the data into Rguroo. But if you have the data already, like I do, you don't have to go that route. You can go to the analysis drop down under analytics, mean inference, 1 and 2 populations. Choose your data set, IQ of first and secondborn sons, and then you have to choose your variables. So we're comparing the firstborn IQs to second-born IQs. So variable 1 is firstborn, variable 2 is second-born, and if you'll look here at the bottom, everything has been filled in for us. I'm going to skip over to 1 and 2 population. We're doing 0.01 significance. I'm going to go ahead and do the confidence level as well. So I'm going to put 0.99 t-stat, unequal variances, 0.01 significance level, and we're trying to say that there's no difference, or that there is a difference. So I'm going to do not equal to 0, not forgetting to click t statistic, and then we'll preview it. And what we're interested in is the confidence interval for later. So write that down, negative 16.1 and 14.3. But let's skip down to the p-value. Wow, lots of shading. So that kind of go ahead and shows you that the p-value is going to be large. So the p-value was 0.8646. That's pretty large. Okay, so we're going to compare that to our significance level of 0.01, and this is definitely larger. So if it's larger, again, we fail to reject the null. And if we can't reject the null, we don't have enough evidence for the alternate. So we're going to say there is not enough evidence to conclude, and then you need to make sure that you write out H1 in context. So there's not enough evidence to conclude that there is a difference in mean IQ between firstborn and secondborn sons. Now, let's check out our confidence interval. So we are 90, go ahead and write it out. We are 99% confident that the true difference in mean IQ scores between firstborn and secondborn sons is between negative 16.1 and 14.3. So really, when you're doing a confidence interval for two populations, you're estimating the difference. Really, all that matters when you're trying to see whether this supports your hypothesis testing conclusion or not is the sign. So we have a negative and a positive, which means 0 is included. So this implies that there's no difference. So isn't that what we just found here? There's not enough evidence to show that there is a difference, so that sort of implies that there's no difference. So that means it agrees. All right. All right, so new post-surgical treatment was compared with standard treatment. 7 subjects received new treatment, while 7 others, the controls, received the standard treatment. The recovery times in these days are given below. So we have treatment times and control times. Can you conclude that the mean recovery time for those receiving the new treatment is less than the mean for those receiving the standard treatment? Standard would be control. Okay, so we're doing a mean inference for two populations, and we would enter our data, and I believe I have the data already typed in for this as well. One moment. All right, this would be, I'm not sure how I would have put this in. Treatment and control. Yes, I believe that's it. So why don't you pause the video and go ahead and enter and save this data set. Okay, so going back, we're going to do our null and our alternate statement. We're doing mean of the treatment group and the mean of the standard or the control group. And so for the null, of course, we assume that they're equal. For the alternate, we're saying that the new treatment is less than the mean of those receiving the standard. So new treatment is less than the standard treatment or the control. If you want to write control instead of standard, you can do that as well. All right, so let's run the test. Oops, I did not mean to do that. Running the test, go to Analytics, Analysis, Mean Inference 1 and 2 Population. Choose your data set, treatment and control. And then variable 1 would be the new treatment. Variable 2 would be standard or the control. And you see it's automatically filled in. Skip over to population 1, 2. If you would like a confidence interval, you can go ahead and do that now. Let me just look. They gave us 0.05 significance level. So I'm going to do 0.95 here, t-stat, test of hypothesis 0.05. We're trying to see if it's less. And remember, we always put in 0 for these. T-stat, unequal variances, preview. All right, so confidence interval, I'm going to go ahead and write that up here on my screen. Negative 18.28 and negative 3.72. And then I'm going to write my p-value, which is 0.0036. Okay, and we are going to go back to the other screen here, and we're comparing that to 0.05. It is definitely less. If it's less, we reject the null. If we reject the null, we say there is enough evidence to conclude that the mean recovery time for those receiving the new treatment is less than the mean for those receiving the standard treatment. All right, so confidence interval. We are 95% confident that the true difference in the mean recovery times of the new treatment group and the control group or standard is between negative 18.28 and negative 3.72. All right, so again, what does that mean, that confidence interval? What does that mean? Well, we have two negatives, so this implies that mean of the treatment is less than the mean of the standard. And that's what this says. There is enough evidence to conclude that the mean recovery time for those receiving the new treatment is less than the mean for those receiving the standard treatment. The two negatives, when you subtract mu t minus mu s, you get negative. So that would be less than 0 because that would imply the first is smaller than the second. So it agrees. All right. King Tut's curse. So this one sounds kind of fun. All right, King Tut was an ancient Egyptian ruler whose tomb was discovered and opened in 1923. Legend has it that the archaeologists who opened the tomb were subject to a mummy's curse, which could shorten their lifespans. A team of scientists conducted an investigation of the mummy's curse. They reported that 25 people exposed to the curse had a mean lifespan of 70 years and a standard deviation of 12.4. I'm going to kind of go ahead and highlight that because I know I'm going to need that in a moment. While 11 Westerners in Egypt at that time who were not exposed to the curse had a mean lifespan of 75 years and a standard deviation of 13.6 years. Assume the populations are approximately normal. Can you conclude that the mean lifespan of those exposed to the mummy's curse is less than the mean of those not exposed? Use alpha equals 0.05 level of significance. So we're doing a mean inference to population again. So let's go ahead and write our null and our alternate statement. We're trying to say that the mean lifespan of those exposed is equal to the mean lifespan of those who were not exposed. I'm going to E for exposed, N for not exposed. And so what we're trying to say is, can you conclude that the mean lifespan of those exposed to the mummy is less than those not exposed to the mummy? So we do less than there. And it's going to ask you for, the sample mean of exposed, the sample standard deviation, and the sample size. It's going to ask you for the mean of the non-exposed, as well as the standard deviation and the sample size. All right, so for the exposed, it was 25 people. They had an average lifespan of 70, a standard deviation of 12.4. For the other group, there were 11 Westerners in Egypt. The mean lifespan was 75. and a standard deviation of 13.6. All right, so let's move on over to our Rguroo mean inference 1 and 2 population. This time we're putting the data in ourselves again. So labeling exposed and not exposed. So sample mean 70, standard deviation of 12.4 for the sample, no population standard deviation, and a sample size of 25. For the second group, the not exposed, we have a mean lifespan of 75 years with a sample standard deviation of 13.6 years and a sample size of 11. And then we click on the population 1 and 2 tab. We're doing 0.05 level of significance, so I'm going to do a 0.95 confidence interval, and I'm going to say that it is less than. Less than what? We always put 0 for these. And choose T statistic. Yep. Preview. So writing down our confidence interval. Our confidence interval is negative 15.0815 to 5.08154. And what does this show you? Negative and positive, 0 included. It implies no difference. All right, so let's go ahead and figure out the p-value. Go back. The p-value was 0.1554, and that is greater than 0.05. And so because it is greater, we can say there is not enough evidence to conclude that the mean lifespan of those exposed to the mummy's curse is less than the mean of those not exposed. And so we can't say that they're different, and up here it's saying that it implies that there's no difference. So I would say that it agrees. If you were going to write the confidence interval in the sentence, you would say that we are 95% confident that the true difference in the mean lifespans of those exposed to the curse and those not exposed to the curse is between negative 15.08 and 5.08. Again, because 0 is included, it implies that there is no difference and agrees with our conclusion. All right, moving on. We're going to talk about some two proportion tests now. We've already talked about how to write the null and the alternate. The biggest difference here is that you use p's instead of mu's. So to perform this test, you would choose proportion inference under the analytics tab and the analysis drop down. You need to make sure that you label the response label and the success label. You do not have to label a failure. All right, so you want to label those, and then you want to fill in the data here and here. And before I forget, you also have to label the population. So you need to label, sorry about that. You need to label the response label and the success label. So, what is the data you're collecting? And what would be considered a success? What is the population that your study is on? And then you would label the first sample for the first population and then the second, and fill in this info here. And then you would click on the test hypothesis tab. If you wanted to do a confidence interval, you'd click on that as well. But under the test hypothesis tab, you would do the alternate statement, the level of significance, and then you would click large sample Z. Okay, so let's look at example, childhood obesity. The National Health and Nutrition Examination Survey weighed a sample of 546 boys aged 6 to 11 and found that 87 of them were overweight. They weighed a sample of 508 girls aged 6 to 11 and found that 74 of them were overweight. Can you conclude that the proportion of boys who are overweight differs from the proportion of girls who are overweight? So since we're doing a proportion, we're doing a proportion inference, and we're doing to population. All right. So for our null, we're going to assume there's no difference in the proportion of boys who are overweight to the proportion of girls who are overweight. But for our H1, we're going to say that it differs. So we're going to say not equal to. And so let's label what we know. We know that we have 546 boys, and of those, 87 are overweight. I'm just going to write OW for overweight. And then you have 508 girls, and then of those, 74 are overweight. And the population is 6 to 11-year-old. Just 6 to 11-year-olds. Just write it like that. Pretty much we have everything that we need, although it does ask about the response variable. So the response variable is we're trying to see if they're overweight or not. So I'm going to say the response variable is we're talking about weight. And a success would be, yes, that they are overweight. I think we've got everything. We're missing a significance level, so I'm going to go with 0.05. All right, so let's go to the other screen. We're going to go Analytics tab, Analysis, Proportion Inference to Population. And the response variable, what we're collecting data on, is weight. And it's a success if they say that they are overweight. The population we're looking at is 6 to 11-year-olds. And the first sample is boys, and the second sample is girls. So sample size for boys, 546, 87 were a success. Sample size for girls, 508, 74 of those were overweight, so a success. Clicking on confidence interval, I just want to go ahead and do that as well. I'm going to do 0.95% and then large sample Z. And for the hypothesis test, we're going to do not equal to, and then this number is always 0 for the two population tests. 0.05 is what we're going with for significance level large sample Z. So I'm just going to write these down. You write them down as well. So my confidence interval goes from negative 0.0297 to 0.0571. and we've got a p-value that is equal to 0.5376. There. All right, so I'm going to compare this to my significance level of 0.05. It is definitely greater. So if it's greater, we fail to reject the null. So if we fail to reject the null, we would say there is not enough evidence to conclude that the proportion of boys who are overweight differs from the proportion of girls who are overweight. So what we're saying is we can't prove that there's a difference. And if we look here, negative, positive, that implies no difference. So if that implies no difference, then the confidence interval supports what our conclusion said. All right, example 2, pollution and altitude, not attitude. Let's see how many more we have. We've got 2 more examples. All right. So in a random sample of 340 cars driven at low altitudes, so I'm going to go ahead and start writing some things down. All right, so we've got 340 cars driven at low altitudes, so low altitude cars, and 46 of them exceed standard of 10 grams of particulate pollution per gallon of fuel consumed. And in a random sample of 85 cars driven at high altitudes, so 85 high altitude cars, 21 of them exceed the standard. Can you conclude the proportion of high altitude vehicles exceeding the standard is greater than proportion of low altitude cars exceeding the standard? Use a 0.01 level of significance. Here's the one thing that I'm going to do here. It says, can you conclude the proportion of high altitude exceeding the standard is greater than the proportion of low altitude? Because of the way they ordered that wording, I'm going to do high altitude is the first sample and low altitude is the second sample. So I'm going to go ahead and put that in there. And we're doing a proportion inference to population, of course. So our null is proportion of high altitude is equal to the proportion of low altitude. And for our alternates, that was H0, not H1. H1, proportion of high altitude is greater than the proportion of low altitude. I believe we have everything we need to run the test. Significance level is 0.01. Write that down. All right, I'm going to go ahead and do both the test and the confidence interval, even though it doesn't ask for one, but I think it's just good practice. All right, response label is, we're talking about whether it exceeds the standard 10 grams. Does it exceed the standard 10 grams of particulate pollution? So I'm just going to say 10 grams pollution for short. And a success is that it exceeds. Population, cars, and the first label is high altitude, and the second label is low altitude. And we're going to fill in our sample sizes. So 340 low altitude, 46 of those exceeded. I'm sorry. Let me go back. I did this wrong. That's low altitude. High altitude, 85 cars were high altitude, and 21 exceeded. And then out of the 340 low altitude, 46 exceeded. For confidence interval, I'm going to do 0.99. Click large sample Z. For the test, I'm going to do greater than 0. And if you look, proportion exceeds for high altitude is P1. Proportion exceeds for low altitude is P2. So we're saying high altitude is greater than low altitude. Large sample Z, and of course we need to change our significance level to 0.01. Click preview. Write everything down. It looks like our confidence level is negative 0.018 if we rounded to 0.241. All right, and we have a p-value of 0.0057. Okay. Going back to the other screen. So this is definitely less than 0.01. So we would say we reject the null. And if we reject the null, that means there is enough evidence to conclude that the proportion of high altitude vehicles exceeding the standard is greater than the proportion of low altitude vehicles exceeding the standard. And for the confidence interval, we would say we are 99% confident. Did we change our confidence level to 99%? We did. Okay, just double checking. We're 99% confident. The true difference in proportions of the proportions between high altitude cars exceeding the standard and low altitude cars exceeding the standard is between negative 0.018 and 0.241. So what does that mean? We have a negative and a positive, so it implies no difference. And that's actually different than what we found. We found that there was enough evidence to conclude that there was a difference, specifically that it was greater. The high altitude was greater than the low altitude. So it's interesting to see that the confidence interval doesn't agree. Let's make sure I wrote down the confidence interval correctly. Oops, I'm clicking the wrong buttons. Let's see, confidence interval. Let's just go back and make sure we did it right. Data summary, confidence interval, 0.99, large sample Z. There's going to be no change. It's between negative and a positive. So yeah, so in this case, they don't agree. And I believe I've told you that occasionally that happens. Most of the times they do agree, but sometimes they don't. So this time they do not agree. All right, moving on. Last example, preventing heart attacks. Medical research performed a comparison of two drugs, clopidogrel and ticagrelor. I probably said those wrong, so I apologize, which are designed to reduce risk of heart attack or stroke in coronary patients. A total of 6,676 patients were given clopidogrel, and 6,732 were given ticagrelor. Of the clopidogrel patients, 668 suffered heart attack or stroke within 1 year, and of the ticagrelor patients, 569 suffered a heart attack or stroke. Can you conclude the proportion of patients suffering heart attack or stroke is less for ticagrelor? All right, so we're doing a proportion inference, and we're doing two population. All right, so we're trying to say that the proportion of those that take ticagrelor is equal to the proportion of those taking clopidogrel. And for the alternate, so the reason I'm putting the T first is because it says that it should be less for the ticagrelor. So I'm going to show ticagrelor proportion is less than the clopidogrel. And again, I'm probably butchering these names. I really do apologize. All right. So let's write down what we know. We know that we have 6,676 patients given the clopidogrel drugs. I'm just going to write C. And of those, 668 suffered heart attacks or strokes. And then there were 6,732 that took the drug that starts with a T, ticagrelor, and of those, 569 suffered heart attack or stroke. And significance level 0.01, and we're saying ticagrelor is less. All right, so analytics, analysis, proportion, inference, two populations. All right, response label is, did they have heart attack or stroke? Question mark. It was a success if they did have heart attack or stroke. And population or patients. And I didn't spell patients right. Patients. And then for the label for the first population is I'm saying it wrong. Ticagrelor. And then the second was clopidogrel. Whew. All right. So the one with the T, there were 6,732, and of those, 569 had heart attacks or strokes. And then of the drug that starts with a C, it's 6676. And of those, 668 suffered a heart attack or a stroke. I'm just double checking my numbers before I move on. All right, so then I'm going to go to confidence interval, even though it doesn't ask for that. And I'm going to do 0.99, large sample Z. And for test hypothesis, I'm going to do less than and less than 0. And I'm doing 0.01. And large sample Z. All right, so looks like we have 2 negatives for our confidence interval. I'm going to write that down. Negative 0.0284 and negative 0.0027. And then the p-value is 0.0009. Okay. So, for the p-value 0.0009, that's less than 0.01. So we're going to reject the null. And if we reject the null, that means there is enough evidence to conclude H1 is true. But we need to write H1 in context to conclude that the proportion of patients suffering a heart attack or stroke is less for tisagrelor than clopidogrel. Whew. All right, so there we go. We finished that. But if we were to see if our confidence interval agrees, let's see what happens. We would say, just to get the practice, we are 99% confident. Let me just make sure I did 99%. I did. 99% confident the true difference between patients suffering heart attack or stroke that took tisagrelor and clopidogrel is between negative 0.028 and negative 0.00. I think it was 23, but I'm just going to leave it 002 because I'm running out of space. Now, what does this mean? They're both negative, so this implies that the proportion of those that took the T drug is less than the proportion of those that took the C drug. And that is what we said here. We said there was enough to show that it was less.